Well, thank you. It's a real pleasure to be back where I thrice belonged. There's sort of 2 points for today's talk. One is to provide a light-hearted entertainment on a hot Friday afternoon. And the other one is to show John and Clark just how little I learned in their realism seminar 25 years ago. So sort of standing behind the talk is the idea that I think the underdetermination arguments, nobody likes them. Everybody attributes to them to von Frosten, and he says he's proud to have never relied on one. But I think actually they deserve more respect than they get, and I think that the realist dismissals of underdetermination arguments are more complacent than they ought to be. So that's sort of the point of the talk, which will become clearer towards the end, I hope. I should have practiced with this thing. OK. All right. So this is a picture of a NASA instrument called GRACE. So it's 2 satellites that just follow each other around in a circumpolar orbit. So they go pole to pole. The Earth spins around. So they go over virtually every part of the Earth pretty regularly. And all they do is keep track of the distance between them. So the following one, let's put it this way. Say they're going over Mount Everest. Because of the additional mass there, the front one will speed up a little bit. And the separation will grow until it's passed, and the other one is going over Mount Everest, and then the separation will go back to what it used to be. So they just keep track of that distance. They beam all the data down. Some themes of data analysis produce models every month of what's going on. The point is to measure the gravitational field of the Earth. And they can do it with spectacular accuracy. So this is all part of the prologue here. They can do it with spectacular accuracy. So for instance, they can see the Amazon basin and the neighboring Orinoco basin are out of phase because they're on opposite sides of the equator. So the rainy season in the Amazon is the dry season in the Orinoco, and vice versa. And you can see those effects using these satellites. Or you can see all the mass disappearing as glaciers melt. Or you can see the a few places on Earth where mass is accumulating rather than disappearing, accumulating rapidly. And you can also see water depletion due to drought or over-irrigation from aquifers. So here's an animation from depicting California during this decade here or so. And as it goes along, you see, sort of the background color is the baseline. Blue is lots of water. Red is too little water. And as you get towards this big drought that ended a year or two ago, it goes all red. And that represents 1 trillion gallons of water that's disappeared from California. OK, so that's the kind of thing you can do with this satellite. By measuring the Earth's gravitational field, you can draw all sorts of inferences about what's going on near the surface of the Earth if you put certain assumptions into your model. OK, that was the first half of the prologue. Let me get rid of the cursor. Here's the second half. So this is, I think, maybe the high point of philosophical discussion in the public sphere, a debate between Ricky Gervais and Stephen Colbert about whether or not God exists. Oh, sorry. So just going to do that again.
We want to make sense of nature and science, and it's too unfathomable that everything in the universe was once crunched into something smaller than an atom.
But you don't know that.
Well,
you're just believing Stephen Hawking, and that's a matter of faith in his abilities.
Yes.
You don't know it yourself. You're accepting that because someone told you.
Yeah, well, but science is constantly proved all the time. You see, if we take something like any fiction, any holy book and any other fiction, and destroyed it, okay, in 1,000 years' time, that wouldn't come back just as it was. Yes. Whereas if we took every science book, right, and every fact, and destroyed them all, in 1,000 years, they'd all be back, because all the same tests would be the same result.
That's good. That's really good.
So
That's really good.
OK. That is really good, right? Like that is a core part of our idea of what science is, that it enjoys a certain sort of objectivity. So let's talk about that. So here's an encapsulation that's like maybe 1 degree more careful than Gervais's, but maybe slightly more grammatical, I hope. According to a common view, science is objective. Anyone following its methods will be led closer and closer to the truth about any given question as more relevant data is discovered. In particular, disagreement among scientists concerning any given question will be transient. Okay, so I'm not saying this is the only notion of scientific objectivity that's floating around or something, but I think it is a core one that is widely shared. And it's the notion that I'm interested in today. So here's another formulation of the same kind of thing from Peirce. Don't be distracted when you think about this by Peirce's views about truth. Those views are motivated by this view about objectivity rather than the other way around. All the followers of science are fully persuaded that the processes of investigation, if only pushed far enough, will give one certain solution to every question to which they can be applied. Different minds may set out with the most antagonistic views, but the progress of investigation carries them by a force outside of themselves to one and the same conclusion. This activity of thought, by which we are carried not where we wish, but to a foreordained goal, is like the operation of destiny. No modification of the point of view taken, no selection of other facts for study, no natural bent of mind even, can enable a man to escape the predestinate opinion. Okay, that's this idea that we have about science. I mean, maybe sophisticated philosophers will often not buy into the whole picture anymore, but this is a sort of core part of what a lot of people think makes science great. So that's Peirce. Okay, here's Steven Weinberg, the physicist. If we ever discover intelligent aliens on some distant planet and translate their scientific work, we will find that they have discovered the same laws. Okay, so this is the same idea: Gervais, Peirce, Steven Weinberg, right? You have to. I mean, Weinberg is being a little. Obviously, he doesn't think if Martians had come to Earth during the period of ancient Greek philosophy, they would have gotten there on spaceships using Aristotelian physics, right? So you may meet aliens and find they don't have exactly the same science as you at a time, but the point is that if you wait long enough, each will catch up with other. Okay, and that's an idea that's really a lot like Peirce's, and Gervais's idea is why we think it all fits together that way. Okay, so I have more slides like this. If there's anyone here who thinks like, that's a wacky notion of objectivity, nobody actually has it, I can bore you with more slides after the talk. But this is a widespread notion of objectivity I'm claiming, and it's the one I want to talk about today. Okay, and what I want to talk about is whether underdetermination is a threat to this form of objectivity or not. So underdetermination, as I'm using it, comes in 2 strengths, regular and extra strength. So regular strength underdetermination is the phenomena where you find any finite data set is consistent with many hypotheses under consideration, but there are methods of inference whose outputs are probabilistically guaranteed to converge to the truth in the infinite data limit. So think about the kind of classic curve-fitting problems that are discussed in 1950s era philosophy of science textbooks, the good ones. You're shown a bunch of data points like this, and you're supposed to conjecture the function whose graph they lie on, the function that encodes the true relation between 2 physical quantities of interest. Right? And for any finite set of data points, there's all kinds of curves you could draw. Right? So logic alone isn't getting you very far. But if the right kind of data points are presented to you, any method you have for playing this game and any method I have will both converge to the true function as the number of data points goes to infinity. And hence, any disagreement between us will also evaporate. Right? So if I like to just connect the dots, and you like to draw the lowest degree polynomial consistent with the data points, at every finite stage we'll have wildly different looking curves, but the difference is going to be evaporating as t goes to infinity, as we see more and more data points. Okay, so that's one kind of instance of regular strength underdetermination. For finite data sets, lots of hypotheses consistent with the data, but if you get if in the ideal limit of infinite number of data points, the underdetermination goes away. Okay. Same kind of thing with guessing the bias of a coin from from knowledge of the outcomes of a sequence of tosses. Right. So if I'm just telling you heads, tails, heads, heads, tails, tails, heads, heads, heads. Right. There's all kinds of rules you could use to infer the bias of the coin. For any finite data set, they'll disagree in general. But the number of tosses goes to infinity, each of them will output a sequence of conjectures that converges to the true bias of the coin, unless the data set, the data stream is misleading, and that's a chance zero event. So we're pretending it can't happen. Okay. Regular strength under determination. But of course, there's also extra strength under determination. So in this is the setting in which all data sets, whether finite or infinite, are consistent with multiple hypotheses under consideration. So it's impossible to construct methods of inference that are probabilistically guaranteed to converge to the truth in the infinite data limit. Right? So if the whole infinite data set is consistent with more than one hypothesis, then there's no way we can be guaranteed to converge to the truth, because our method is going to have to pick one of those hypotheses. But if one of the other ones is true, then we didn't get to the truth. How could this happen? Well, a sort of toy way it could happen is if the data, in the curve fitting case, if the data points we're shown aren't the right kind. So say I'm only shown, this is the x-axis, and I'm only shown data points that lie to the left of the origin. Right? I don't find anything out about what happens when x is positive. Then obviously, I'm not guaranteed to converge to the truth. Right? I'm never going to find out anything about what's going over here, over here. Or in the coin case, another toy example, if I ask you to guess not the, or if I ask you to guess both the bias of the coin and its denomination, there's no method that's guaranteed to reach the truth. Right? Because you're not finding out anything about whether it's a quarter or a dime from finding out what pattern of heads and tails comes up when it's tossed. Okay. All right, so two kinds of underdetermination. Now, let's talk about something that's obviously related but is conceptually distinct: inverse problems. They won't get tied together until the following section. Oh, yeah, that's the vascular structure of a pigeon head. It's some kind of fancy CT scan. And in fact, I think it's from an ad for some kind of agent you can put in your pigeon's head. So that when you use this kind of CT scan, you get this beautiful structure that's just telling you about the veins and nothing else. Okay. So that's typical of a kind of thing that's done in like all medical imaging and much of geophysics and wide swath of astronomy and astrophysics. We have a distinction between direct problems and inverse problems. Right? So the direct problem, we fix the laws and the internal structure of some object that we're interested in. And then we use the laws and the fixed laws and the known internal structure to generate, to determine the set of measurements that we would make exterior to the object. Right? So if I tell you, here's Newton's laws, and here's the actual internal structure of the Earth, then you can determine what the gravitational field should be at each point on the Earth's surface. The inverse problem is to go the other way. So given the laws and the outcomes of the measurements made exterior to the body to determine its interior structure. And that's what our medical imaging machines are doing. Right? They're just shooting a bunch of rays through you, compiling the data, doing some kind of analysis, and then spitting out these pictures that are telling you about the internal structure just based on measurements made external to the object. Good. So this is a piece of terminology that's a little idiosyncratic, but it will save time. I'm going to say an inverse problem is solvable if, given a complete data set collected exterior to the body, there's only one internal structure consistent with that data set. So this is saying that you have uniqueness for the inverse problem. I'm just going to call that solvable for convenience. Okay? I'm going to say it's unsolvable if, given a complete data set, sometimes there's more than one internal structure consistent with that data set. Okay, so here's a mathematical fact. Many, or maybe most, inverse problems are unsolvable. Okay, it's not a sharp claim that most inverse problems are solvable. You'd have to set up some incredible framework in which you could talk about the whole family of inverse problems and so on. But it is a rule of thumb that people in geophysics, for instance, seem to be committed to. And part of what's going on is the more nonlinear or complex the laws that you're fixing are, the more likely it is that an inverse problem is going to turn out to be unsolvable in this sense. Right? It's only when things are really, really nice, linear, well-behaved, that you expect the inverse problems to be solvable in actual applications. OK, so here's an example of a solvable inverse problem, X-ray tomography. So this is what things like CT scans do. They, what we ordinary people call an X-ray is they take a bunch of X-rays and shine it through your body. They have a piece of film, and they print out, they develop the film. Right? So all the X-rays they're shooting at you are coming from one direction and going through your body parallel to each other, to a good approximation. What these people call a radiograph is one of those. So multiple radiographs means they're shooting X-rays through from this direction. That's one radiograph. Then they also shoot them from some other direction. That's another radiograph, and so on. Then they analyze the data from multiple radiographs to try to reconstruct what's going on inside you. So this was a non-trivial part of applied mathematics in the 1970s. Somebody won a Nobel Prize for doing this. And it turned out that what they had done was basically rediscover some things that had been done in the teens by pure mathematicians. So it's very interesting. Okay, so here's a sort of survey article lecture that one of the guys involved in this was giving in 1977, published in the Bulletin of the American Mathematical Society. Practical and mathematical aspects of the problem of reconstructing objects from radiographs. The determination of the determination of an object by X-rays and the lack of it, section 4. One of the main points I want to discuss in this article is the extent to which X-rays determine an object. This seems to be widely misunderstood, and the misunderstandings seem to have led in unprofitable directions. Okay, so he thinks people misunderstand the facts, the mathematical facts, about whether or not the inverse problem of reconstructing the human body from knowledge of radiographs is solvable or not. So theorem 4.1. An object is determined by any infinite set of radiographs. So great, right? If you went to the doctor and they shined X-rays through your body from an infinite number of directions, took all that data and computed it, they would actually know for sure what's going on inside you. Right? That's a nice theorem. Right? Theorem 4.2. A finite set of radiographs tells us nothing at all. And the commentary on theorem 4.2, for some reason, this theorem provokes merriment. OK, so here's theorem 4.2 stated more precisely. People who are interested can read through this. But what it amounts to is basically take an object, like my head, let's say. Take my head, and take finitely many radiographs of it. There's an object that's just like my head that will give exactly the same radiographs if you take them from the same directions, except it has a big empty chunk in some part of my head where there is not an empty chunk. And that's true for any finite set of radiographs. And of course, the actual medical imaging machines are only taking finitely many. So there's some trick we use to get around this problem in practice. We can talk about that later. But this is the fact that we, theorem 4.3. OK, that was a solvable problem in my sense, right? Because if you had the full infinite data set, you could reconstruct the interior. Here's an unsolvable inverse problem, the all-time classic gravimetry, trying to determine the density of the interior of the Earth, the way it varies, from knowledge of the gravitational field at the surface of the Earth, or from Grace. Okay. And here's a classic contribution from Stokes in 1867. It's one of those articles that has a bit of personal narrative. Somebody was bugging me, and I replied by referring to the well-known property of a sphere, according to which a central mass may be distributed uniformly over its surface without affecting the external attraction. By applying which proposition to the mass such as the Earth, we may, evidently, without affecting the external attraction, leave a large eccentrically situated cavity absolutely vacuous, the matter previously within it having been distributed outside it. Okay, so the point here is one that was familiar to Newton. if you take a uniform solid sphere and look at its gravitational field, you get exactly the same gravitational field from a point mass concentrated at the origin, or from a homogeneous shell, or indeed from any spherically symmetric distribution of the same amount of matter. And Stokes is saying, yeah, so now just go somewhere in the Earth, pick any little ball you want, and take all the matter inside it and spread it over the surface. You're not going to be able to tell that that happened from outside, so maybe the Earth is hollow. Blah, blah, blah. It is known further that the mass of a particle may be distributed over any surface whatsoever enclosing the particle without affecting the external attraction. So now he's saying you don't have to do it over spheres. You can do it over potato shapes. And in this way, we see at once that we may leave any internal space we please, however eccentrically situated and however weirdly shaped, wholly vacuous. Okay, and this is, even if we know the gravitational field at every point on the surface of the Earth, we can't determine the distribution of matter within the Earth. So that's an unsolvable inverse problem. Good. So back to objectivity. So, I mean, you can sort of see the connection between the previous two sections, right? We talked about inverse problems and, you know, like measurements exterior to your pigeon, measurements exterior to the Earth. And if those were the only measurements you could make, then we'd find out something about underdetermination, right? Because underdetermination is what is possible at all, not just what's possible doing a certain kind of measurement. So if the in principle available evidence about human heads were restricted to exterior X-ray attenuation data, the medical imaging would be an example of regular strength underdetermination. Now, in fact, we have other ways of finding out what's inside people's heads, right? And so it doesn't count as an example of even regular strength underdetermination, because the finite set of data you collect can be like, cut open the head and see what's in it, right? OK. But if we couldn't cut open heads, right, then this would be a nice example of regular strength underdetermination. And similarly, if we couldn't break open the Earth, then gravimetry would be a good example of extra strength underdetermination. Okay. But we can cut open heads, and we can break open the Earth. So this stuff about inverse problems doesn't really quite engage yet with the stuff about underdetermination. OK. But for some objects, even the in-principle evidence must come from the region exterior to them. So I'm thinking like stars, for instance. I'm thinking we can't make direct measurements of the interior of a star. Okay. But you could be like, oh, but what if we did the X-ray thing, right? That was only, is this going to get us all the way to extra strength underdetermination? No, because think about the X-ray thing. If you take an infinite number of radiographs of a head, you find out exactly what's in the head. Why couldn't we do that to the sun? Okay, you couldn't use X-rays because the sun is sort of hot enough that it's opaque to even high-energy photons. What about neutrinos? That's what you're thinking. This is an interesting case of something, a scientific idea that migrated from science fiction novels into the scientific journals. So around 1970, some guy wrote a book in which there was neutrino tomography of stars, this kind of idea. And now you can find like people at the Institute for Advanced Study like writing about like maybe this is a technique we'll be able to use one day to find out about the interior structure of the sun. The sun is not hot enough to be opaque to neutrinos. So you could use neutrino tomography to find out the internal structure of the sun. But there are things hot enough to be opaque to neutrinos. So newly formed neutron stars are an example. Okay, so I'm sticking with that as my example. There are some objects that we can't find out about the interior of because they're too hot or something. We can't find it out directly. And also, the kind of techniques that we have for finding out indirectly about their internal structure appear to involve unsolvable inverse problems. So we have extra strength underdetermination, which places a limit on scientific objectivity. Some scientific questions are intractable and convergence to the truth about them can't be guaranteed. Okay, so far it's just a little tiny point, right? Things like newly formed neutron stars. And when I say newly formed, it's like a very, very brief initial segment of their lives. They have this feature. OK, but that's the threat for now. OK, so what are we going to do about the threat? So there's two things we could do. We could either restrain science or restrain objectivity to make the threat go away. So here's a first kind of thing that people say. Properly understood, science is not concerned with extra strength problems, problems in which there's extra strength under determination. So you can read Reichenbach as saying this. You can read Ehrman as saying this. You could read my colleague Liz Anderson as saying this. Mark was telling me last night you can read Duhem as saying something like this. Okay? The idea is we should take a first-rate attitude towards the outputs of those parts of science that are guaranteed to converge to the truth, and an alienated second-rate attitude towards the other. So these people have this general idea. They spin it out in different ways. So for Reichenbach, it's all about what are you willing to act upon. For John, it's like what kind of attitude are you taking towards your credences? Are you sort of wholeheartedly embracing them, or are you somehow like distancing yourself from them? OK, so I think that's a really attractive idea. In fact, I believed this for a long time, but I don't believe it anymore. That this is a good idea, this part. And the reason is as follows. So suppose you're being shown a binary sequence bit by bit. So nature does this to us all the time, right? It sounds artificial, but of course, a lot of the data we're being presented with can be crushed down to this form. Suppose you're being shown a binary sequence bit by bit, and you're asked both to identify the sequence you're being shown and to guess whether it's the binary expansion of a rational number or an irrational number. OK, so it turns out the first task is really easy. All you have to do is just guess. At each stage, you just guess something that's consistent with the data you've been shown. And then you're guaranteed to converge to the true answer in the limit. That's just like this kind of game, where as long as the curve you draw always passes through the data points you've seen, as the number of data points goes to infinity, if they're properly distributed, you're guaranteed to converge to the true curve. But there's no such methods for the second task. So many people in the room will have seen this kind of thing before. It's familiar, for instance, as a form of Proposition 12 of Kelly and Gleamore, convergence of the truth and nothing but the truth. If people want, we can talk about it later, but I don't want to stop now to convince you about this. But it's true. There are no methods guaranteed to converge to the truth, no matter what binary sequence you're being shown about this kind of thing. And I think it's also intuitive, right? If somebody says, let's play this game, I'm going to show you a binary sequence, and you have to guess whether it corresponds to a rational number or an irrational number, you're just not going to be able to do it because anything you see is consistent with either answer. And you never really get any real information about what's going to happen in the future. OK. So back to our proposal, remember? What it said was, take a first-rate attitude towards those outputs of the method, towards the outputs of those methods that are guaranteed to converge to the truth, and an alienated second-rate attitude towards the other ones. So in this case, the Reichenbach idea is telling us to take a pro attitude towards this one and a alienated attitude towards this one. Right? We're like, I've seen a bunch of data, and I'm confident in my guess about which sequence I'm being shown. But don't ask me whether you're showing me a rational number or an irrational number. Like that's the kind of thing I don't expect my methods to be able to guess. Right? But that's putting you in a really unfortunate situation, right? Because if you really believe if you really believe your conjecture that it's a certain sequence you're being shown, then surely you should also really believe that that sequence is rational if it is a rational number, and it's irrational if it's not. Right? The problem is your answer to question 1 implies an answer to question 2. So if you say, yes, I believe my answer to question 1, but don't ask me about question 2, there's a really bad failure of logical closure of your beliefs or pragmatic attitudes or whatever. Okay? So this is to say, you should be confident or whatever in your belief concerning the true identity of the sequence, but agnostic or whatever concerning whether it encodes a rational number or not. So you're like, yeah, I think it's definitely all zeros. Don't ask me whether it's a rational number or not. It sounds bizarre. It's analogous to Newton saying, I've discovered that gravity varies inversely as the square of distance, but being unwilling to say whether or not it varies inversely as the square of some polynomial or other. There's a deep problem with acting like this. In particular, people have always complained that Reichenbach, oh yeah, he's able to vindicate the scientific method, but it's not very satisfying because he vindicates at the same time all kinds of other terrible methods that we hate. But the truth is he doesn't even manage to vindicate the scientific method because the scientific method does not have this kind of failure of closure. OK, so that's why I don't like reply 1. Reply 2. OK, so constraining science didn't work. Why don't we constrain objectivity instead? So at the beginning, I said, oh, objectivity means you converge to the truth. And in particular, disagreements between scientists evaporate. Why don't we give up on the truth part and just stick with the evaporate part? So we're going to be less ambitious about what objectivity is supposed to be. So the idea would be, properly understood, scientific objectivity requires the convergence of opinion of scientists, not convergence to the truth. So how could this be? Well, either there's just one scientific method of inference for handling any given problem. Right? Then all scientists have to follow it, so of course there's no disagreement. Or there are many admissible methods, but any disagreement between them evaporates in the limit, which isn't to say you get to the truth. Maybe all the methods are destined to get to the wrong answer in some cases. OK, reply 2 also doesn't work, I believe. So given any method for guessing whether the sequence being revealed encodes a rational number, there will be a second method, that locks onto the truth in the limit in every case in which the first one does, but also in some additional cases. And this is true even if we restrict attention to Bayesian methods, as some people might like to. OK, so from the point of view of convergence to the truth, any method m is dominated by some other method m star, which is in turn dominated by m double star, and so on without end. There's a whole hierarchy of better and better methods from the point of view of convergence to the truth. So remember, the view under consideration is, oh, either there's only one method, or there's only one admissible method, or they all agree asymptotically. All the admissible methods agree asymptotically. And what this is saying is, well, if there is one really good method, then there's also a bunch of methods better than it. Or if there's a bunch of methods that agree asymptotically, say they agree with this, well, they're all dominated by m star, because m star is better than m, and these things all have to agree with m in the limit. So according to the view under consideration, only one, m or m star or m double star or whatever, only one of these methods can be scientifically acceptable. Right? That's the core of the view. But in that case, I think it's natural to say, well, why should I care about being scientifically acceptable? I've got a better method that gets to the truth in more cases than yours. Like this just doesn't seem relevant to me. Another way of putting this is how would the ideal method be singled out? Presumably by some sort of trade-off of tractability and breadth of convergence to the truth or something, right? And then what? You're going to say to some being who wants to use a trade-off that leads to a method that converges in more cases, oh, you should live down to our standards. It doesn't seem like the way to go. OK, so I think objectivity is indeed undermined. So this is what we have so far. Scientific objectivity has its limits. Whenever our in-principle evidence about a system is limited, in principle, sorry about that, to a certain sort of indirect evidence, which does not allow us to reconstruct the hidden structure of the object. OK, so this is a small limit on scientific objectivity. If we're interested in a kind of object that we can't investigate its interior structure directly, and the kind of techniques we have for investigating its interior structure indirectly have unsolvable inverse problems, then there's extra strength underdetermination, and there can't be a guarantee of convergence to the truth. But you should be thinking, yes, but it sort of sounded like uncontentious examples were scarce, right? We had all that song and dance about proto-neutron stars. If that's the only limit to the objectivity of science, maybe I'm not so worried. Right? So far, all I've got is scientific objectivity is frayed a little around the edges, and maybe just a little, right, around the edges. Good. And then the handout ends, because there is a punchline, but I didn't want people who read ahead to get to it. Let's try to make this into a more exciting, more global threat than we have so far. So let's go up a level in abstraction and think about science itself as the mother of all inverse problems. Okay, so presumably there's some, inverse and direct problems were set up. In the direct problem, there's a map K that takes you from, given the laws, takes you from the possible interior structures to the total external measurements. And there's a map K inverse that tries to go the other way. Or you try to show that there's a map K inverse that goes the other way. Let's think of science as involving an inverse problem. So that means there has to be a corresponding direct problem. Here's a description of it. Presumably, there's a map K that takes as input possible ways the world could be and gives as output the set of observations that would be made were the world that way. Okay, so total theories. You give me the total theory of the world. I crank through with some math, and I tell you what observations would be made if the world were that way. Science is the inverse problem. From the total set of observations that will ever be made to determine the relevant unobserved structure of our world. Okay, relevant in here is like, I don't want you to say, oh, I don't care about certain things. Okay, put in whatever you care about. Unless you only care about things that will be observed, you've still got an interesting inverse problem here. So remember the foreshadowing from before. Many ordinary inverse problems are unsolvable because the salient hidden aspects of the target system can't be reconstructed from the accessible evidence, even in the infinite data limit. So surely it's natural then to wonder about this inverse problem. Is it solvable? Well, it's natural to worry that it won't be, since in practice most inverse problems aren't solvable. And a good sign that an inverse problem isn't solvable is if the direct problem is nonlinear or complicated in some way. And this looks like an extremely complicated direct problem. So I claim we should expect the inverse problem to be unsolvable. And so we should thinking of science as a grand inverse problem, we should expect it to be unsolvable. And hence, we should think that there is here a real threat to objectivity. At any rate, I claim the burden of proof would appear to rest with advocates of scientific objectivity. Here, as in ordinary cases, it appears reasonable to think that the more complex the forward problem, the less likely it is that the inverse problem should be solvable. Sorry, I've switched from direct to forward, but same thing. OK, so that's the threat. Now, the epilogue is going to take us back to realism instead of objectivity. OK, so here's the standard argument against realism from underdetermination. Underdetermination of theory by evidence is endemic, says the anti-realist. Many or most theories have empirically equivalent rivals. And then they say, evidence can give us no reason to believe one rather than another pair of empirically equivalent theories. And then they say, so we should have little confidence in the truth of even our best scientific theories. This is, I think, the form in which the argument is rehearsed most places, the most common form of the argument. And realists have some very standard responses that you can also see rehearsed most places. It turns out that most of the times this argument is rehearsed, it's being rehearsed by a realist who wants to complain about it. And these are the standard complaints that they're itching to make and why they wrote that section of that chapter. Right? They want to say underdetermination is a fantasy, not a scientific reality. Or they want to say, this whole notion of empirical equivalence relies on it's all keyed to this distinction between observable and unobservable, but that's an epistemologically inert distinction. Why should that distinction between what we can see and what we can't see matter so much in our theory of knowledge? Or they want to say, and I think this is the most interesting one, they want to say just because two theories are empirically equivalent doesn't mean that the evidence gives us equal reason to believe them. OK, so as you may have gathered, I deny one. I don't think underdetermination is a mere fantasy. And there are interesting scientific cases of underdetermination. They may not be. I don't want to say it's endemic, but I also think it's an exaggeration to say it's a mere fantasy. And I think 2 is a distraction from my perspective. The way I was doing things in the preceding section, the inverse problem that is science concerned the distinction between the observed and the unobserved rather than the observable and the unobservable. Like, I just don't think the anti-realist needs to rely on that particular distinction. There's lots of other ways to set things up. I'm not saying that's either of those points are conclusive, but that's my story, and I'm sticking to it. And part of the point of the talk is to bring out what I think is unsatisfactory about 3 as a response to this argument. Okay, so the point of the talk is to get realists to admit that objectivity fails, and then ask them how good they feel about 3 when they're trying to keep that in mind. So I think the question I'm posing to realists is realism without objectivity satisfying, really? So think about it this way, like think about the real cost of 3. So remember what 3 said. Just because 2 theories are empirically equivalent doesn't mean that the evidence gives us equal reason to believe them. Right? So the key notion here is evidence. Why do you believe that? The evidence gave me that reason to believe that. Right? Why don't you believe this one? The evidence didn't give me the reason. I would have liked to believe it, but the evidence just didn't give me that reason. It didn't give me any reason to believe it. That's the attitude. OK. So let's think about 3 in the following terms. Yeah, so I'd like Mark to avert his eyes while I draw the space of all theories. OK. The grid lines are telling us about empirical equivalence. OK, so this is the space of all theories, and 2 theories get to be in the same box if and only if they're empirically equivalent. OK. So consider the case of a Bayesian agent with a reasonable prior facing extra straight underdetermination. So, and let label each of these boxes E1, E2, E3, and so on. OK, so those are classes of empirically equivalent theories, and each one gets a non-zero probability. So we've thrown away all the ones that got 0 probability. For a given prior, right, one of these reasonable priors, go through and in each box pick, in E1, let A1 be the theory that prior gives highest probability. And let B1 be some other theory that gets positive probability. Then go to this box. Let A2 be the one that gets highest probability according to that prior. And let B2 be some other guy that gets positive probability, and so on. So for each box, you pick the winner according to this prior, the one that gets highest probability, and you call that A. And you pick some loser, B. Okay, and then we think about these propositions, the disjunctions of all the AIs and all the BIs. Each of these, A and B, are contingent propositions that get non-zero probability according to the prior, each of them. But there's no evidence our agent could see that would convince her that A was more likely than B because of the way we've set things up. Right? If the evidence rules out one of these boxes, it rules out AI and BI, they both go. If the evidence doesn't rule out one of the boxes, then they're both in there, and the A guy is always going to get more probability than the B guy. So when we take the disjunction of the live A's and the disjunction of the live B's, the A thing's going to win every time, no matter what evidence we see. Right? So I want to ask, is this really a case in which we're entitled to say, oh, the evidence gave me reason to believe A rather than B? It seems like it was your starting point that determined your preference for A over B. And that preference is an initial bias that can't be destroyed by evidence at any time. There's no kind of evidence you could see that would lead you to think B was more likely than A. Right? So it doesn't really seem just to say, oh, my response to the underdetermination argument is the evidence gives me reason to believe one or the other of these empirically equivalent things. Like here we have 2 empirically equivalent things, and it doesn't seem like it's the evidence that's giving you the reason to believe it. A is more likely than B because you are unwilling to ever believe that B is more likely than A, no matter what evidence you see. It's your starting point, not the evidence, that's determining your preference for A over B. OK. This is my second last slide, but it's a good one because it's Peirce again. OK, so here's Peirce. Now, there are some people, among whom I must suppose that my reader is to be found, who, when they see that any belief of theirs is determined by any circumstance extraneous to the facts, will from that moment on not merely admit in words that that belief is doubtful, but will experience a real doubt of it, so that it ceases to be a belief. To satisfy our doubts, therefore, it is necessary that a method should be found by which our beliefs may be caused by nothing human, but by some external permanency, by something upon which our thinking has no effect. Okay, so this is like Peirce's dream that seemed reasonable when he wrote this in 1878 or something like that. Okay? But I'm claiming, actually, this is a poignant summary of the human condition. I think if you're being intellectually honest, you feel the pull of the first paragraph. But I think it may actually be impossible to live up to the standard that he sets in the second paragraph. OK, that's it. Thanks very much. And
thank you, sir. I appreciate it. Have a wonderful day. Thanks. I'm sorry, Bruce. I just need to sneak past you. Sorry, guys.
I think it did say 3:30, but it just stuck in my head as 3. Are you on the calendar?